to the end of this short repetition. When we want to transform particular point or a set of points, it's enough to calculate transformation for every point separately. Is this true for all of you? If there are no sound? Okay, so we can combine transformations. So we can perform, let's say, a set of rotations and translations in, arbitrary order. Okay, it depends on the purpose or application, but when we combine them, so we can of course calculate the intermediate stages, but we can represent it as a matrix multiplication. So in this case, when we multiply all transformation matrices before multiplying the localization of point A, we get a single transformation matrix for any complex set of transformations. So this is a very important feature because it's enough to calculate this transformation matrix once, and we can apply it for all points on our scene. Maybe it's not clear for you why I talk about geometrical transformations, but look, the most now in computer graphics, the most scenes are 3D, so they are represented as some objects in 3D space, and somewhere in this space there is a camera. And now to render the image, we have to calculate the position of every point, every vertex, or every object with respect to camera position. So even the particular point in global coordinate system is here, for example, but when we have camera and the camera is somehow oriented, the image or scene will be transformed. So we have to calculate it. If the camera is moving, we have to recalculate it after every shift. Okay. Similar to homogeneous transformation, we have something which is called axonometric projection. So axonometric projection let us to calculate the image which will be created when we perform a projection of three-dimensional object on a two-dimensional plane. So in this case, probably you have something like that in your secondary school. So if we have plane and we have 3D object, it's enough to project every point on this plane, and then we can connect these points, and we get the resulted effect. But axonometric projection can be, calculated. So the position of every point on two-dimensional plane can be calculated also by using matrix multiplication. So it's enough to know what is the position of the point in three-dimensional space, and we have to have a projection matrix and the offset. of the projection plane. So the projection matrix represents the orientation of the matrix with respect to 3D coordinate system, while the offset represents the shift of this plane with respect to the origin of coordinate system. So using this multiplication, we can somehow squeeze our 3D scene into two-dimensional case. Of course, in case of axonometric projection, there are no perspective. So it's typical for technical draws, and but usually when you have some, you know, games or other 3D renders, we have a perspective transformation. So it means that the objects which are farther from the focal point are smaller. Yeah, it is due to that the camera is a pinhole camera. So there is a single focal point, and the camera has a view angle. So the farther from the focal point, we can observe the larger area. So in this case, to calculate the localization of particular points on two-dimensional plane, we have to calculate the cross-section between line which goes from the focal point to every vertex. So this cross-section, which will be marked on projection plane, creates the projection of particular point. Yeah. So again, so similar to axonometric projection, it's enough to connect these points, and we get the perspective transformation effect. Yeah. Of course, here you have some mathematical relationship. You don't need to, you know, learn it by heart. Yeah, because okay, it makes no sense. But in computer graphics, both the axonometric projection and perspective transformations are quite popular. So you should understand what it is and how it works, you know, mostly in geometrical way. Okay, so these are two technologies which are used to make the image flat, because it doesn't matter the scene is 3D or not 3D. The final effect, which is rendered on the on display, has to be two-dimensional. So if we have camera on our scene, we have to, or computer has to perform the perspective or axonometric projection to make it flat. Okay. The third element, which is vital for computer graphics, is texturing. So I don't know, probably some of you have an experience in computer graphics, in texturing and other things. I'd like to talk about this issue, which is quite complex issue. Yeah, so for example, Blender. Shortly, so look. Let's assume that we have the square object. But this square object, we can think about that this is a side of the three-dimensional object. Yeah? We can have cube, for example, or any other object. And we want to put the texture on it. But even this object is square when we perform, for example, perspective transformation or even axonometric transformation, and the camera is located not perpendicular to the plane of the surface, we get the object which will be geometrically deformed. Yeah? So after perspective transformation, it will be deformed. In fact, texture is a bitmap, so it's not a vector object, it's only set of pixels. So having texture, we have adjusted this texture to particular region. So let's assume that we have object like this, and in the texture is okay. It depends on the method we use. We use affine transformation. We set the texture after projection. So after the process is, or transformation process or projection process is finished. So in this case, we know that there are 4 edges, and the texture has to be fitted along these edges. So look, the texture is fitted along this edge, this edge, this edge, this edge, but because the edges has different dimension, it is squeezed or stretched. So looking only on the particular side of this object, it looks okay. But because the sizes are different, there is a problem in the middle. So look here, you can observe, a virtual edge. It doesn't exist because this surface is flat. But it seems that there is, a virtual edge. It is due to way how the projection, so this affine mapping was done. So look, affine mapping is very very fast method, so it's quite easy to apply because we need to consider only the 2 vertices to calculate this squeeze factor for mapping. But the problem is that it looks not realistically. The second possibility is using perspective correction texturing. So look here, we have the bitmap, which is properly mapped. So we can observe even the perspective effects where the elements which are near to the camera are bigger than these elements which are farther. Yeah, UV mapping. Okay, let's. Yeah, so in this case, the transformation process is much more difficult because we have to also take into consideration the 3D position of this element with respect to camera. Yeah? So this mapping has to be performed in, let's say, in 3D space, and then it can be, projected. So instead of 4 points, which has to be projected, we have more, intermediate points, which has to be projected to properly project this bitmap. So it significantly increased the mapping cost. So probably, I don't know, but probably in computer games, you have a set of parameters which led to set what should be, how texture should be mapped. Okay, it influence on the realistic effects of the game, but also it in the case when the effects are more realistic, it consumes more graphic cards power. Yeah. Okay, so that's all about methods. Now I like to tell you something about displays or monitors. I start from, ancient or obsolete technology, but it's still somehow some elements are still used in LCD display or in OLED displays. Okay, so probably I think that you remember the CRT monitors. So that was monitors which were not so narrow like the monitors now are, but they have a cathode ray tube. So yeah, like but what was typical here, that the system was quite complex because it consisted of the electrons GAN, which produced a stream of electrons, and this stream was sent to place which was called a luminophore, so the number 7. So when the particular electron was hit the luminophore starts to blink. Here we have the set of electromagnets which were responsible for controlling the position of electrons stream, and they were used to move the stream line by line. So the effect was that the image was drawn by this electron ray. Yeah? Because the latency was not so high, and the luminophore or the pixel on luminophore blinks for, let's say, several milliseconds or maybe less, the effect was that the whole image could be observed, and it could be refreshed quite often. So let's say 50 up to 100 hertz. So look, it seems that the system was quite complex. Yeah, so there were a lot of elements, and because we have to control the position of the electron ray, this displays, CRT displays, has to be not so narrow, because in this case it could be very hard to control the electron ray position. But what is maybe not important, but typical for this displays, and it is still used in current displays. It is horizontal and vertical synchronization. So image was drawn line by line. So this time is called horizontal sync. So after drawing line, the image was silently, the array was silently moved to the beginning of the next line, and so we have here a h-sync period. So the period in which the beam is not working, and the magnet moves it to the beginning of new line. And the second synchronization was vertical synchronization. So it's called V-sync. So it was time in which the ray was moved from the end, the right bottom corner to the origin of the display. So it takes time. So in this place we have something which is called V blank. So V blank is time when the ray is moved from the end to the beginning. This V blank is still used in LCDs and in other devices, even it is not required because they works different, but it is still used to synchronize displaying images. I will tell you something about this later. Okay, so now let's try to talk about LCD displays. Of course, some manufacturers told or tried to impose that LCD is, is obsolete technology because now it's LED. But in fact, the displays which are presented as a LED displays, they are still LCD. Yeah. I tell you something about LED displays or OLED displays later, but now how it works and why it's so narrow. So look, the LCD displays consists of several elements. So the first element is a backlight. So this is a plane which generates uniform white light. For example, on some laptops like Mac, you can see the backlight because on the in the case there is, a lot of the manufacturers which, when you turn your laptop on, it starts, so it's the light is visible. So in fact, this is a backlight which you can see from the opposite side. Then we have a polarizer. So what polarizer does, it passes only the light which electromagnetic vector orientation is homogeneous. So probably you have some tests with polarizer during your physics classes in secondary school. So when we have two polarizer and they are oriented perpendicular to each other. So one of them pass the light with polarization 90 degrees, and the other is oriented, you know, perpendicular. You can see that the effect is that nothing should be should pass. Yeah, and when we reorient the polarizer, so we start to turn one of them, we can see that it led us to increase the brightness, yeah, of the light which pass. So, but in LCD displays, we have two polarizer which are oriented perpendicular. So in fact, no light should pass. Yeah? So if we have backlight, and the backlight will be polarized by the first polarizer, and then we have the perpendicular polarizer, nothing should pass. Of course, because the polarizers are not perfect, you can see that even our display, let's say, is black, it isn't black, it is gray. Yeah? It is due to that the polarizers are not perfect. So even they are oriented perpendicular, they pass some fraction of the light. Okay. Between polarizers, we have two layers. So the first layer is liquid crystal layer, which is deposed on the TFT layer, so transistor on-off layer. So how it works, or what are the liquid crystal? Yeah, liquid crystal display. Liquid crystals are, it depends on the device, but they are organic substance which is able to twist light polarization. But it twists light polarization when the voltage is supplied. And the twist angle depends on the voltage value. Okay? So using this transistor on-off layer, we can control the twist of a particular or the twist of the light vector in separate and quite small region. Mam wykład, przepraszam. Okay, so this is the method which can be which is used here. So look, if we are able to twist the light vector in restricted region, we can control the light intensity, because if it will be twisted by 90 degrees, in theory, all light should pass through the perpendicular polarizer. It is not twisted. The polarizer should stop this light, so the pixel should be black. Okay, but you can see that the backlight is white, so it has white color. So now how the colors are obtained. So after liquid crystal layer, we have RGB color filter. So it looks like here. So the system is able to control the brightness of each composite. So here, these three elements creates a single pixel. And if we are able to control each element or brightness of each region independently, we can create or we can generate any color based on RGB mixture. So in this case, we get a color LCD display. So these displays are quite compact, so they are narrow, but you can see that the control system has to be very complex to control every pixel independently. If you have 4K monitors or 8K monitors, you can see how many pixels has to be here, okay? And for every pixel we need to have three independent regions, yeah, to generate color. Okay, so but it is done. It works. Okay, so this technology seems to be very very useful. So now the most monitors which are sold are presented as LED monitors. So it suggests that every pixel is a separate LED. And in fact, for most displays, it is not true. The most monitors which are presented as LED monitors, it means that they have a backlight. Oops. They have a backlight which is generated by LEDs. So there are diodes which creates a backlight. So there are no so many diodes as the number of pixels, but definitely less. Yeah. So there are several types of LED monitors. So-called LED monitors, so edge LED monitors. So the LEDs are located around the display, so on the edge of the display, and the backlight is created by some special layer, which similar to optic fiber, which is able to conduct and disperse light. The second kind, which is denoted as dynamic LED, creates a backlight. So there are some regions on the display. So LEDs are located on the whole surface of the display. And the regions which are black can be generated by turning off the LEDs in particular region. So we are not able to, turn off every pixel, but we can turn off part of the image. So in this case, the black is more black, let's say. So it means that when we turn off the backlight in a particular region, it seems to be true black, not gray, like for most of LCDs. But still, we have liquid crystal layer, polarizers, and so on. Okay, in this meaning, the LED monitors, the true LED monitors are, for example, telebeams or outdoor advertisement displays. So you can see that there are power LEDs and every LED can blink, but look, it is impossible to create using semiconductive LEDs. It is impossible to create a monitor in, let's say, 4K or even full HD resolution because the sleds are quite big. Yeah. So most computers monitors are still LCD. So in fact, the technology which led us to create a true LED matrices, it is called OLED. Of course, Samsung has technology which is called QLED, so it mimics OLED, but in fact, QLED technology is LCD. Yeah, so, but okay, the OLED matrices are the most popular application of OLED matrices are in mobile phones. And there are some, displays or TV sets with OLED, but they seems to be quite expensive now. So how it works? So in this case, we don't have polarizer, we don't have a crystal layer, but we have the two conductive layers, so cathode and anode. And between them, we have the semiconductor layer, but it is not based on silicon, but on organic surface. So in fact, we are able to print this surface using special ink printer. So in fact, every pixel is a LED diode. It's very thin, so you are able to print this elements directly on elastic film or almost any surface. And the effect is that we are able to control every pixel separately. So when the power is on for a particular diode, it starts to light. So the benefits are that the view angle is and contrast is better, yeah, because when the pixel is turned off, it's black, yeah. When it is turned on, we can, by controlling the voltage, we are able to control the brightness of the pixel. So it's quite cheap to produce, but there are some problems with high-scale manufacturing process. So the huge displays has some bugs or problems. So this technology is still quite expensive. The problem is also a shorter lifetime of the LED. So look, you buy a mobile phone, let's say 1 times per 2 or 3 years, yeah. While when we have TV set or computer monitor, okay, we use it for a longer time, a period of time. Yeah? Because this is organic surface, it is also more humidity sensitive, so the surface has to be kept in safe condition or isolated from some environmental effects. But in fact, it is true, LED display opposite to LCDs. So I think that this technology will be much more and more popular. But remember that comparing to LCD, this technology consumes more power. Yeah. So of course, okay, it depends on size and other factors, but the same monitors of the same size in theory, the OLED should consume more power than standard LCD monitor. Okay, so that's all about displays. Now I'd like to start talking about graphic cards. So I showed you some, elementary transformations, but in the middle between graphic card and the display, there is something which is called a frame buffer. So in graphic cards, the scene is represented in three-dimensional space. And then when it is rendered, and it is then represented as an image. And this image is stored in memory, which is called a frame buffer. So when display wants to refresh image, it performs its, every, so the refresh frequency depends on the display, but it's from 60 to let's say 200 hertz. So when the display refresh image, it takes pixels from the memory, graphic card's memory, which is called frame buffer. So a refreshing image relies on taking values pixel by pixel, row by row. Okay. So when the refreshing is finished, the new refreshing cycle starts from the origin of this image. So from the top left pixel. But because frame buffer stores the render effect, it may happen that when the image is rendered, the part of the old image will be displayed, and then it will be changed by graphic cards or modified by graphic cards. So in this case, in synchronization cycle, the one part of the image belongs to the older frame, and the new part of the latter part of the image belongs to the new frame. So of course, it happens in one synchronization cycle. So in the next cycle, everything will be okay, but our perception is quite sensitive for such effects. So we can observe some, blinking effects. So it seems that this image is, quite strange. Okay, so this especially visible when you try to animate something and you use a frame buffer. But I will tell how it is solved. So so remember that if we have the frame buffer size determines the display resolution, and it determines also the color depth, so the number of bits per color. So when we change image or display resolution, in fact, we change the amount of memory which is allocated for frame buffer. Okay, so how it can be solved to make animation not more fluent, because the fluency of animation depends on graphic cards performance and other factors which are not related to frame buffer. But when we have these effects, this effect is related with quality of the animation. So look, in this case, instead of single frame buffer, we can use double frame buffer approach. So how it works? It means that we have two frame buffers. So we have two areas in memory which can represent the output image. And one of these buffer is called back buffer, and other it is called front buffer. So how it works? In front buffer, or in back buffer, sorry, in back buffer, the image is prepared. So the process of rendering creates elements and makes some shadow shading, and okay, it doesn't matter. So it prepares the scene to display it. While in front buffer, the image is displayed. The current image is displayed. So when the image in back buffer, so a new frame is ready to display, so the rendering process was finished, the buffers are swapped. So the back buffer becomes a front buffer and front buffer becomes a back buffer. So in this case, when we switch them, we are able to there are no, blinking effects. But what is more important? The swapping is synchronized with VLAN time. So it is synchronized with the period when the image refresh process is finished. So then when we switch buffers in this period of time, a new image will be printed. So there will be no effects that the part of the frame or image belongs to the older frame and is farther part of the image. So using double buffer mode, this I will show you, talking about OpenGL, I will show you how we can use it. Using double buffer mode, we can achieve the better quality of animation. Okay. So now several information about something which is called GPU. So in modern computers, we have, in fact, not a single CPU, single processor, but we have many processors. So one of them is called GPU, graphical processing unit. So the computer processor is general purpose processor. It let us to perform many, operations, but GPU is the processor which has specialized units. So in fact, as in CPU, we have, let's say, 4, 8, or 10 cores or threads. So we have 4 or 10 processors which are able to perform some operation simultaneously. In GPU, we have hundreds or thousands of processors. They are not so powerful as CPU cores are, but there is a lot of them. So looking at this scheme, you can see that there is a lot of stream processing units. So a lot of cores. which are able to process data at the same time. So the question is, why we have so many stream processing units? The answer is that, look, because the scene is 3D and we have camera on this scene, so the 3D scene consists of vertices which are connected, or the relationship between them is defined. So we have vertices which are connected with some neighboring vertices. So they create 3D shapes. There are textures which are assigned to particular sites, and so on. So look, if we want to process this scene and we want to generate the output image, for example, we have to multiply all vertices by camera transformation matrix, by camera perspective, and so on. So in this case, because we perform this operation on pixels, or not pixels, on vertices, we can do it simultaneously. So every vertex can be transformed independently. If we talk about texturing, okay, in case of texturing, we have to consider a set of vertices, but still the subset, not all vertices, but subset of vertices which belongs to particular site. So in this case, we can perform texturing also simultaneously for every site, let's say, independently. So therefore, we have so many stream processing units, because the graphical operations are highly parallelized, so we can perform it in parallel. Of course, there are other elements. So we have, let's say, render backends. So we have less number of render backends, because rendering process, when we have to consider lights and some shadows and other reflection effects, it turns that, okay, we have to analyze this scene, globally, or the regions are bigger. So in this case, this process is not so high, cannot be performed in so high parallel, but so we have less amount of this peripherals. Okay, but because GPU has so many cores, you can see here, for example, it's not the newest one. Now we have 3080 family, which is quite popular, but it is GTX Titan X. So look, the scheme of this graphic cards look like this. Every green rectangle corresponds to core. So in this case, we have more than 3,000 cores, which can be used to perform this operation independently. Of course, it can be used for rendering, for 3D scene processing, but it can be also used for some parallel computing. So probably you heard that it can be used for Bitcoin mining and any other application like password hacking. So for application in which we have quite simple set of operations like matrix multiplication, but we have to perform a lot of operations like this, and they are independent. Looking at TDP, total distributed power, or deliver power. So look, current CPU processors has TDP less than 100 watts. In case of graphic cards, they have more than 200 watts. Even there are graphic cards which consumes, let's say, 500 watts or more. I don't know whether Bitcoin mining is legal or not legal. I don't do it, but you know, it's. I think for graphic cards is one of the most common applications. So you can observe that the prices of graphic cards increased in the past several years. Mostly that, and okay, the most powerful graphic cards is hard to buy because they are used for cryptocurrencies mining. Yeah, so that is true. Whether it's illegal or legal, okay, it doesn't matter. Yeah? Okay, so look, when you have a graphic cards like this, you should understand why it's so many cores there, what is the reason, or what are the benefits. So how we can, yeah, okay, so now I'd like to tell you or show you something which is called a GPU pipeline. So how the image processing is performed in graphic cards. So GPU pipeline, so this pipeline is implemented on GPU processor. So it doesn't utilize, or maybe a little utilize only the CPU processor, but these stages are performed mostly in GPU. So when we have a scene and we have the all elements like materials, textures, and so on prepared, this process is performed in GPU. So it is called GPU pipeline. It starts from something which is called an input assembler. So we have set of vertices. So our objects are represented as a set of vertices with relation defined. And this is the input. Then we have a vertex shader. So vertex shader performs a geometrical transformation. But in fact, maybe it will be here. It's better visible here. So vertex shader performs operation on vertices. So we calculate some parameters. So the position with respect to camera, the textures which should be applied for particular region, the lighting. So there is a calculate the global lighting, for example, index. Then we have a geometry shader. So in geometry shader, the relationship between vertices are considered. So, for example, in this case, also texturing and lights are analyzed. The perpendicular direction to surfaces is calculated. The light direction with respect to surface is calculated, and so on. So this is the geometry shader. And final, maybe not final, but next stage is rasterizer. So up to this point, everything is based on the vector representation. So we have points in 3D space. Now we have rasterizer. So how rasterizer works? So look, here we have vertices, and then rasterizer tries to calculate the value for every pixel inside. Yeah, so here we have vector elements, and here we have a pixel elements. So after rasterization, the pixel shader is run. So rasterizer pixel shader are usually treated as these are treated as a single stage, but the effect is that we get the value of every pixel on the image. Up to this point, we have only values which are, attached to particular vertices. As I told you, if we have powerful GPUs, so GPU with many processing units, many cores, we can create the programs which are directly run on GPU. So of course, if we create three-dimensional scene, okay, it is also executed on GPU using GPU pipeline, but we can create our own dedicated software. Yeah? So GPU has dedicated AP and libraries which let us to create programs in C++ or other languages. And these libraries are called, for example, OpenCL or yeah, okay. So the most popular is OpenCL, but of course, the very common application, from my perspective, very common application of GPU is something which is called a deep neural networks. So we can easily run or create huge and very complex neural networks and run it on GPU. So they are extremely fast, so faster than it will be run on standard CPU. And they use libraries like TensorFlow or PyTorch, and this libraries has some backends which let to implement or send these elements to GPU and calculate them directly there. Okay. Yeah. Maybe it's not so important now. Okay, we have several minutes. I will be continue the topic about graphic cards or graphic applications later, but I'd like to tell you something about OpenGL. So OpenGL is a library or a language, we can tell, which let us to run or create three-dimensional scene directly in GPU memory and use the methods which are implemented there. In case of OpenGL, the OpenGL let us to create a geometric primitives, so points, lines, polygons, also image primitives like textures, And it let us to create lights, materials, colors, and so on. You can see that OpenGL pipeline is similar to GPU pipeline because it can be run in this pipeline directly. So graphic cards are able to interpret OpenGL commands by hardware. And when we use OpenGL library or DirectX library, it let us to make CPU load, to reduce CPU load, because every commands are run on GPU. But I will show you how, or what are the possibilities of using OpenGL, but maybe not the problem, but in fact, OpenGL is very low-level library. So in fact, we are able, it's extremely fast, but we are able to, generate a very low-level primitives. So to use it easier and to create objects on the higher, complexity level, we use not only OpenGL, but we use some intermediate libraries. For example, GLUT. So it let us to run or use OpenGL, easier. So the first thing is what we are able to achieve in OpenGL. So what we are able to draw. So in OpenGL, we are able to draw the set of primitives which is listed here. Nothing more. So you can draw a single vertex, a set of lines, a line stripe, a GL line loop. So the this chain is closed. A GL polygon that depends between GL line loop and GL polygon is that it has filled interior, so you can define what is the color of it. You can GL triangles, triangle stripe. Yeah? So look, there are no cubes, spheres, and any other complex three-dimensional objects. So to do more complex objects, you have to use these primitives, and you can build from these primitives more complex objects. So therefore, we usually use a higher level libraries to make it simpler. The second issue is that, look, there are no, we have only straight lines. So there are no arch or any polylines. Everything is defined using straight lines. So in this case, it means that to achieve a smooth, rounded surface, you have to use a lot of vertices. And you have to approximate it by short straight lines. Okay. Okay, I think it's time to finish. Today, you have a quiz prepared. So you can log in to a course and you can try to solve this test. So thank you for your attention. And we have a next lecture on Tuesday. Huh? So goodbye.